So here's number 2 in an occasional series of proofs that I'm going to make when and if I feel like it. And it's a classic, it's Pythagoras theorem. So I'm going to start off with a big yellow square with a smaller white square inside it. But I'm going to rotate the white square into the yellow square until it makes 4 triangles. Now those 4 triangles are similar triangles. In fact, they're congruent triangles. They're all exactly the same triangle, and you can appreciate that from the rotational symmetry of how we obtain them. So they're 4 identical triangles, and I'm going to label one of the sides of those triangles A, and of course they're all the same A, and I'm going to label one of the other sides B. Now these are right-angled triangles. We know they're right-angled triangles because we can see that the corners are in the corners of a square. So I'm going to label the longest side H for the hypotenuse of the yellow right-angled triangles. And I'm going to think about calculating the area of this whole figure. Now I'm going to start off with the yellow triangles. One of the yellow triangles, of course, would just be a half times base times height. So that's a half times A times B. And we've got 4 of those. So 4 half ABs. And then the white square in the middle, that's just a square that's H by H. So it's H squared. So the area of the whole figure is 4 times a half AB. That's just the 4 yellow triangles, plus the H squared in the middle. Now 4 times a half AB simplifies to just 2AB. So the area of the whole thing is 2AB plus H squared. But there is another way we can think about calculating the area of this, and that's by just looking at the length and the height of the whole figure. The length of the whole figure is A plus B, and the height of the whole figure is A plus B. So we can calculate the area of the whole figure just from A plus B times A plus B. So multiplying those 2 brackets out, that's A squared plus AB plus another AB plus B squared, or A squared plus 2AB plus B squared. So that's 2 expressions for the area of the whole thing, the one that we calculated first and the one we just calculated, and they're essentially both the same as each other because they're both 2 different expressions for the area of the whole thing. So let's think about those 2 expressions, and we're just going to equate them together. So these 2 things are the same as each other. They're both the area of the whole figure, the whole yellow square with the white square inside it. So for any such square, 2AB plus H squared is equal to A squared plus 2AB plus B squared. Well, we've got a 2AB on both sides of that, so we can just take that away from both sides, leaving us with H squared equals A squared plus B squared. Now, thinking about what the A, B and the H were, the A, B and the H were just the 2 shortest sides of a right-angled triangle, the A and the B, and then the H was the hypotenuse, the longest side. So in other words, we're saying that for a right-angled triangle, A squared plus B squared is equal to H squared, where H is the hypotenuse and A and B are the 2 shorter sides. That argument we made with the square could apply to any size of square placed within a bigger square. So it applies for any right-angled triangle, and it is, of course, Pythagoras theorem. So there we are, we've proved Pythagoras theorem in 4.5 minutes.